Hi everyone! Today we're going to study Z-transform of some standard sequences. Let us define Z-transform. If the function u sub n is defined for discrete values n equals 0, 1, 2, and so on, and u sub n equals 0 for n precedes 0, then its Z-transform is defined to be, this is our notation, Z-transform of u sub n. Also, we can use the notation u of z. This is equal to summation from n equals 0 up to infinity of the function u sub n times z raised to negative n, whenever the infinite series converges. Let's go now to Z-transform of some standard sequences. Number 1, when we have the Z-transform of the function a raised to n. A here is a constant. This is equal to z all over z minus a. Let us show the proof. Suppose we have this Z-transform of a raised to n. By definition, we write summation from n equals 0 up to infinity of the function a raised to n times z raised to negative n. We can rationalize this negative n exponent of the z, and we combine with this a raised to n. Simplifying, we can show that this is equal to the fraction a over z raised to n. We can expand this summation into like this: 1 plus a over z plus the fraction a over z power 2 plus, and so on. We can see that this is a geometric progression of this form, where the sum is equal to a all over a minus r. Using this formula in this progression, the first term is 1, and the r value is the a over z. So this is equal to 1 all over 1 minus a over z. We can simplify this complex fraction, and we will reach the value z over z minus a. So we are able to show that the Z-transform of a raised to n is equal to z over z minus a. Second, when we have the Z-transform of the function n raised to p, this is equal to negative z times the derivative with respect to z of Z-transform of the function n that is raised to p minus 1. Let us show the proof. Let us write the Z-transform of n raised to p. By definition, we write summation from n equals 0 up to infinity of the function n raised to p multiplied by z that is raised to negative n. This n raised to p we're going to split into like this. That is n that is raised to p minus 1 times n. Also, the z that is raised to negative n, we will split and show that this is equal to z raised to negative n minus 1 times z. Look at this z here. It has nothing to do with the n value, which means the z here is taken as constant. We can pull the z in front of the summation here. So, here we go. And then we simplify this negative n minus 1 in the exponent. It will be negative of the quantity n plus 1. This is the Z-transform of n raised to p. This is our equation 1. Now suppose we have another Z-transform of n that is raised to p minus 1. Using our definition of Z transform, this is equal to summation from n equals 0 up to infinity of the function n that is raised to p minus 1 multiplied by z raised to negative n. Suppose we will take the derivative of the z transform of the n that is raised to p minus 1. On the right side, it will be like this. Summation of n equals 0 up to infinity. This n raised to p minus 1 is a constant, so we'll just copy it here. Then we will take the derivative of the z raised to negative n. It will be negative n times z raised to negative n minus 1. Next thing to do, this negative of the n, we will put this negative on the left side. So it will be like this. Then we will simplify the exponent of z, that is negative n minus 1. Let this be our equation number 2. And from here, we will substitute the left side value of equation 2 in equation 1. So here it is. By substitution, equation now becomes z transform of the function n raised to p equals z times the quantity negative of the derivative of the z transform of the function n that is raised to p minus 1. When we simplify the right side, it becomes like this. We're able to prove that the z transform of the function n raised to p is equal to negative z of the derivative with respect to z of the z transform of the function n that is raised to p negative 1. So we're going to use these two formulas to prove other z transforms. Example, let's evaluate the sequence z transform of 1, z transform of n, and z transform of n squared. Let's begin with z transform of 1. We're going to use the formula z transform of a raised to n is equal to z all over z minus a. We can rewrite it again as z transform of 1 raised to n. So the a value here is equal to 1. Using the formula, we have now this z all over z minus 1. This is our answer. We will go now to the z transform of n. Our formula a while ago is the z transform of n raised to p equals negative z of the derivative with respect to z of the z transform of the function n that is raised to p minus 1. In our example here, that is the z transform of n, we can see that p is equal to 1, which means using the formula, it becomes like this. We substitute 1 in the p value. So here it is 1 minus 1. This n raised to 0 is simply 1, which means this is the z transform of 1. The z transform of 1, we have this value a while ago in the first problem. We substitute this value in here. It becomes like this. We're going to take the derivative with respect to z of this fraction. By using the quotient rule, it becomes like this. Let us simplify the numerator. It becomes negative 1. Then we multiply the negative z by negative 1. The answer now is z all over the square of z minus 1. This is the value of the z transform of n. Let's go now to this z transform of n squared. We will use the formula here. The p value is 2. By using the formula, it becomes like this. So 2 minus 1 is 1. Simply we write n. So we have here z transform of n. We have this value a while ago when we solve it in here. we will substitute this value for the Z transform of n. Now we will use the quotient rule to simplify this derivative. Observe that in the numerator, there is a common factor, that is the Z minus 1. When we factor it out, we have now this Z minus 1 multiplied by, in the first group, what remains is the Z minus 1. In the second group, remains is the negative 2Z. We can cancel the Z minus 1 and the Z minus 1 that is raised to power 4. Later, this power 4 becomes 3. Then let us simplify this group and it becomes negative Z minus 1. Let us multiply this negative Z here in the numerator. We have now Z squared plus Z all over the cube of the binomial Z minus 1. This is the final answer.